Hello everyone. We, the students of Rutgers University, New Jersey, are going to present our capstone design project for the class Capstone Design ECE. Our project title is Smart Office Access System. The group members are Ibadullah Qureshi, Sanjida Nasser, Shanila Chaudhary, and myself, Sudarshan Srinivasan. The advisors of our project are Dr. Roy Yates and Dr. Hubertus Franke. Access control systems allow employees to restrict access to certain areas of their building, setting varying levels of security depending on individual employees and clearances. That's why our smart access system is to the rescue. We use facial recognition acting as an authorization key. The administrator is notified in case of any unauthorized access. Basically, the administrator can also remotely unlock the door through an app. We have also decided to think on two-factor authentication for administrator. Recovery mechanism for all authorized users are also being developed. Now we move on to task allocation. Basically, we divided our project into smaller modules considering to establish a cloud connection with Arduino microcontroller at its first place. Basically, we have to connect the Arduino to the Google Cloud using the Python serial monitor, the PySerial. Then we try to create a user interface to store images of authorized users to the cloud database, which pre-processes and sends live video data to a Python script on the cloud. Then after that, we employ our facial recognition techniques to determine authorized/unauthorized users. Basically, we are going to code a facial recognition program using Python and which will work under cloud while live detection and recognition would be happening simultaneously of all the images which are taken from the camera. Then after that, we unlock the door for authorized users if there is a match. If there is not a match, then there are two options. Either the door won't open or you, the administrator, will have a control of the door which we have thought of building an app that will remotely unlock the Arduino lock. This is our overall project block diagram. Basically, you can see on the left the camera, the Wi-Fi module ESP8266 and the Arduino lock are all connected to the Arduino. We prefer to use the Arduino Uno and which is connected to our local server, which is our local laptops or desktops, where we have our local directory and a with a graphical user interface, a GUI. Then we have our Google Cloud Storage, which takes in the images as well as our Python script, which we wrote on the facial recognition algorithm. So basically, there is a simultaneous process. In a nutshell, a camera takes the image. The Wi-Fi is responsible for creating the connection between the Arduino and the Google Cloud. Then after that, the image is transferred from the Arduino to the local server via a GUI. From the GUI, it goes on to the local directory, and then it goes on to the Google Cloud Storage. At the same time, the facial recognition algorithm, where we do live detection and recognition, the code is also transferred to the Google Cloud. The Google Cloud simultaneously handles both the image data and the facial recognition algorithm at the same time. After both these processes are complete, if there is a match, it again points back to the Arduino where it goes on to open the lock. If there is not a match, then it won't open. The lock works like a machine, state machine, where it would be at 0, which is it would be locked. But we always have a backup for everything. It's going if there is someone unauthorized who tries to enter, then we can create a secure two-factor authorization, which would be going to their email IDs, or we have a lock opening app which is on our phones, which from where we can have the authorized users can have the access to open or control the door. So this is our overall project block diagram.
So phase 1 consists of image transfer to cloud storage. As can be seen in the phase-specific block diagram, the camera is connected to an Arduino Uno that is then connected to a local server. Within that local server, there is a GUI that comes with the camera, which runs the camera and continuously saves images onto a local directory. This process will be shown soon. In the background, there is a PowerShell script that automatically and continuously uploads images in that local directory onto a Google Cloud storage bucket that will then be useful for the phases to come. So for instance, we start with the camera. We use a 2 megapixel ArduCam Mini module SPI camera and made the appropriate connection to an Arduino Uno board. After we've made all of the proper connections as shown in the block diagram, we run the ArduCam GUI. The GUI consists of several camera options such as turning the camera on and off, pixel options, different functions and filters, and singular and continuous mode. Singular mode means that every time the capture button, now replaced with the stop button, is pressed, a photo is taken. Alternatively, continuous mode will record the screen and save images of the frame through time until the stop button is pressed. There is also the option to save images onto a local directory. Here it can be seen that our camera is turned on, our mode is set to continuous, and our photos will be saved in the arducam_pics directory. The local directory is shown to the left of the screen and the GUI is on the right. A script that will be shown later is running on an alternate screen that uploads the files from the local directory into the cloud storage bucket. The camera is running and photos are being uploaded to the directory, as you can see. When I sit down in front of the camera, there are now pictures of my face that can be used for the facial recognition stage. And then when I am no longer in front of the camera still captures pictures of the empty setting. This script runs in the background, which takes the pictures from the directory onto the cloud. And here's the cloud storage bucket that is continuously updated with images as they are being taken.
Phase 2, we are going to discuss about facial recognition, in which we are going to run a facial recognition Python script that performs detection and recognition of images using OpenCV libraries. The code is written on a local server initially in PyCharm IDE, and then it was loaded to the Google Cloud. As photos are continually taken by the camera, the script will perform live detection and recognition on the images saved on the cloud. Now we would move forward to explaining about what is the purpose behind detection and how does it work. This is the facial recognition block diagram in which the input image is taken for facial detection. After that, it goes for another liveness detection where it determines whether the image is real or fake. If the image is real, it goes for the recognition where you are decided to choose for authorization or not. If you are authorized, then after that you are granted access. If you are not, you are denied, or the recovery mechanism is triggered. If the image is fake, automatically you are denied access or it will trigger the recovery mechanism. Detection is basically when you try to detect the image and you want to find whether the authorized person is allowed to pass or no. Basically, detection works on the OpenCV module. We have used this module called cv2.cascade_classifier, which is an OpenCV module which inputs a har classifier of which contains a random number of facial detection objects in an XML file. After that is taken, we load it in, we create a variable and we input that cascade classifier. After that, then we start to convert that image, whichever we have taken in the camera, to a grayscale image because it's easier for the algorithm to work. After that, we create a region of interest. Why we do that is basically a region of interest is necessary. If there are a lot of people in that image, we have to detect that one person which is necessary to authorize or to make that person pass through the door. Especially this is a very useful thing in crowded scenarios. After that, in order to lock down the region of interest, we make like a rectangular frame, which is easier. We can even make circular frames, but we prefer a rectangular frame.
Liveness detection is an anti-spoofing technique used in facial recognition systems. Liveness detection ensures that an image or video of an authorized user does not fool the facial recognition system. We can set up a liveness detector by treating it as a binary classification problem with two classes. Number 1, real faces, and number 2, fake or spoofed faces. The next step is to build a dataset. The real face dataset is the set of faces detected from the frames of a video recorded from a mobile camera for each user. The fake dataset is the set of faces detected from the frames where the video of the user spoofs the recording camera. The fake dataset can be extended to printouts and high-resolution prints. Another component needed to train the model for liveness detection is the convolution neural network, called liveness-net. This network will have as few parameters as possible to reduce the chances of overfitting on our small dataset, and ensure our liveness detector is fast and capable of running in real time. Using the dataset and liveness-net, we can train a liveness detection model with OpenCV, Keras, and deep learning. The final step is to combine all the pieces and run the trained liveness detector on each face detected in the data obtained by the Arduino camera and classify as real or fake.
Now we discuss about recognition, in which we use local binary patterns histogram algorithm, also known as the LBPH algorithm. After that, firstly we convert the image into numpy arrays. Each pixel will contain a specific number and the image will be an array, a numpy array. After that, we train the algorithm with the images stored on the local server. After the training is done, we import an LBPH recognizer tool, which is already available as a pre-made tool. After that, once the recognition happens, it matches basically the image which you have stored on the local server versus the image which is sent by the camera. After the matching is done, accordingly the decision making happens.
Our final stage is our app-controlled lock.
We are using facial recognition to allow access to authorized individuals, and if the face is recognized, then the lock will unlock, and if not recognized, then an alert will be sent to the administrator, and the administrator can remotely unlock the door using the Blink app. The block diagram of the lock mechanism is shown here. It is either the face is recognized or the signal from the Blink app is used to unlock the door. When the system controller unit receives instruction, it will drive the 5-volt relay module, which is the switching unit, and the 12-volt solenoid lock will be unlocked. In this video, it can be seen that I'm unlocking and locking with the help of the Blink app.
So how will this benefit business? Business office's number one priority is security of the office building and their employees. Today, employees must have some sort of key or swipe access to get into the building, and visitors must go through extra security measures such as security check or just to wait in the lobby until someone gets them from inside the building. Our system makes this process faster and more efficient by authorizing employees facially so that they no longer have to carry a key or a card and risk losing it or having it stolen. It also can give temporary access or allow visitors in remotely using the app, which reduces waiting time. It can also be used to track who has tried entering the building as a second level of security. We'd like to thank you so much for watching our video, and special thanks to Dr. Roy Yates and Dr. Hubertus Franke, who have helped us so much throughout our semesters of Capstone.